Okay, so let's get started with what we were looking at last time. We were looking at Bayesian concept learning, right? And so we're going to now kind of make it a little more general. So in the last class, if you remember, we were looking at this very interesting experiment that we did, in which I gave you a bunch of concepts, and then I gave you some data, and I asked you, tell me which concept generated this data, right? And here the setting was fairly simple because there were only 10 concepts. So you could enumerate all the probabilities and then choose the one that's the best. But the next question was that what do you do after you have learned this concept, right? So the way we want to use this is, as I showed you much earlier, we are going to use it for classification, right? But in this setting, the way we want to use it is that once you have learned what the concept is, I give you a new data point and you have to tell me, did it come from this concept or not, right? So that's kind of the classification task, right? So we have set it like this. So I give you a new input x star, and the question that you have to answer is, what is the probability that x star is also generated by the same concept as D, right? So this is sort of, we have written it in a different way, but it is kind of the same question that we ask any classifier, right? We give it a new x star and then say, is the class 1 or not, right? So it's the same thing. Is the probability, so what is the now since this is a probabilistic classifier, so we don't ask for 0, 1 answer, like is it this or not. What we ask for are probabilities. So what is the probability that x star is also generated? So if this probability is high, then we will say, that yes, this is generated from this concept, right? So the way that works is that, of course, now I only give you D. D is your training data, right? Now, first option is that you can say, I'm going to use the prior probability as the most likely concept. So let me use the paper here. So the question in the concept learning that we are asking all right, is that given a new x star, what is the probability of x star to be generated by the same concept given your training data, right? Now, what do we have so far? We have a prior probability distribution over all concepts. So we said that there are 10 concepts, right? So H1, H2, all the way to H10. So in this case, the probability distribution are actual numbers, right? We can say, okay, the probability, now this goes from 0 to 1. These are the probabilities. So the prior probability of this to be the concept is this much, this is maybe this much, and so on, right? So this is what we call a probability distribution. The next thing, so this is prior. The next thing that we computed was the likelihood of the data given the given a concept. So then so this is P of H, this is prior. This is P likelihood of the data given some H. So it could be something, depends on what the data is, right, and so on. And then what we did was we looked at the posterior probability, P of H given D, as you would have done in your gradients quiz as well, is that then this is some revised estimates of probabilities. I don't know what these are, but okay. So this is posterior. So we saw how to do this in the last class, right? This is what is given to you. This is the prior probability distribution over all concepts. This is the likelihood of the data set given each one of these concepts. And this is the posterior probability of each concept given the data set. So these are linked, right? So this is basically, these both are the distributions over the concepts, right? But this is before you have seen anything, this is after you have seen the data. That's why we call it posterior. So now, but the question that I'm asking you is, what is the probability of a new data point to come from this data, right? So approach number 1 is choose the most, the most probable concept using P prior, which means that use the prior distribution and choose the concept which has the highest probability. So in this case, maybe it's H1, right? And then say what is, so then you say that P of X star equal to C given D is nothing but P of X star equal to C given H1, because H1 is the most likely, right? So that is one possibility, one way to do it. The second way would be choose the most probable concept using likelihood. Right? So choose the concept which gives you the biggest likelihood. Let's say this is H1, H2, H3, and dot dot dot. Let's say this is H9, H10, right? So we choose H9. So then our probability becomes given H9, because H9 has the highest likelihood, right? And then the next could be, let's say this is H8, H9. Next could be choose the most probable concept using posterior. All right, any questions so far? So these are three ways you can do to compute the probability of a new data point, right? But there is another way. So I'm going to talk about a fourth way, which is called Bayesian averaging, okay? Because all right. So to motivate why we need Bayesian averaging, let me sort of give you a little more description of this. So let us say all of these concepts are like experts, right, which are telling you something, yeah? So in the beginning, think of these as 10 wise people sitting in a room, right? And this distribution tells you which one is, which one has the best knowledge about the problem at hand, right? As you observe the data, this posterior has the revised sort of weightage of each expert, right? So right now it seems like the H8 would be the best expert, right? So this third approach says choose the wisest expert, right, according to this distribution. However, the drawback of that is that you are kind of ignoring the knowledge of all of these other experts, right? So all you're saying is let's choose this expert. Now, if the distribution was something like this, if the distribution was everybody was close to zero and this expert was so high, right, then it's fine, right? Then it's okay to use this expert's knowledge because that sort of is has most information anyway, right? But what if your distribution was like this? Everybody was kind of equal, this guy was slightly up, and that's right. In that case, this approach would choose this one, right? However, that is not a very, you're kind of wasting all of this knowledge, right? You're wasting the expertise of these other experts who are slightly below everybody else, right? So to do that, so how do we kind of incorporate the knowledge of all the experts when you're making next prediction? That is done by doing what we call Bayesian averaging. So in that case, what you do is we say P of X star equal to C given D is an average of probability of H I. So I goes from 1 through 10. Let's say you have 10 experts, right? Times probability of X star equal to C given HI. So instead of choosing one expert, you say I'm going to use the information that is provided by each one of the expert, but I'm going to weight it by their individual probabilities, right? So what essentially happens is that you're going to use every one of their knowledge, but you're going to weight it by their heights of these bars, which means that if there is an expert who has very high probability, then you give that expert more weightage, right? If you look at this example, what will happen in this case is that all of these probabilities will be close to 0 for all of the other ones. So it is nearly equal to just using this expert. So then this and this might be the same, but this, the answer will be fairly different because now you are using the probabilities of all the other ones, all right? So that is what I had in the slide. So any questions? So yes, go ahead. Probability of right. Oh, sorry. Yeah. So this has to be the posterior because you are using this distribution, right? Yeah. Any yes.
You said it's an average.
Yes.
So you should divide it by 10, right?
Right. Well, so I meant average, but it's kind of doing the average here because it's multiplying this value here, right? So remember that if you divide it by the total sum of these, this is 1 anyway, right? Because all the probabilities sum up to 1. So it's kind of doing the averaging automatically. It's a statistical weighted average, not the general arithmetic average. Anything else? Any other questions? Or yes.
Mathematically, what would be the second term?
This term? This is basically the probability of observing this new data point given this hypothesis. So for example, let's say, let me give you an example, all right. So example. So let's say your D was something, right? So let's say your D was what we looked at last time, 41664, right? So when you compute your H, and let's say your H, your concepts were all those concepts that we looked earlier. So it gives you an estimate of the probability posterior for each one of the concepts, right? So that is something, right? Some of them are high, some of them are low, right? Now let's say your new data point is 2, right? So each concept here, there will be a probability of observing X star, which is 2, given each one of these concepts, right? So probability of seeing 2 when the concept is all even numbers would be something. So that is the value that goes here. All right? Yeah.
And for the first term, it says the probability of the hypothesis or the data point, what do we take that as in for this particular graph?
So that would be each one of these values. So this is the posterior probability for each H, right? This is how much, given this training data, what is the probability of each one of these H to be the concept. So that is how you read it, right? So that you use that in this term. So you use that in this term, and this is basically given the concept, what is the probability of that data point. So if the concept is even numbers, you'll have some probability and so on, right? Any other questions? All right. Fantastic. So I'm going to switch here to this. Right. So this is the option number 3. So I numbered them option 0 because typically we don't use this as an option, right? This is you're not using a training data at all. So that's not, it's kind of a trivial option. But other ones are used everywhere. So MLE is a maximum likelihood estimate. That's if you're using the likelihood. Map is if you're using the best posterior, and this one is if you're doing an averaging overall, right? So that is a very classical Bayesian approach. If you are a frequentist statistician, you'd probably just stop here. You'll just take the best one over there. But a Bayesian statistician would say, everything is likely. So let me just take a Bayesian average of that. All right. So now we are going to go one step further, right? Now we are going to say, what if, so see, so far we looked at, 10 concepts, right? Our hypothesis space had 10 concepts. But as some of you might have followed a little bit of a thread on Piazza about infinite concept space, right? So what if instead of having 10 concepts, we have infinite concepts, right? So I'm going to explain that in the context of this simple example. Let's say we are trying to learn a generative model for a sequence of coin tosses, All right. So let's say I show you some coin tosses. I show you 4 heads and a tail, right? And I want to ask you what is the distribution that generated it, right? In sort of a normal language, it means that can you tell me the probability of heads for that coin, right? Because every coin is associated with the probability of heads. If it's a fair coin, of course, it's half, but in general, it could be anything, right? So we typically model that as a Bernoulli distribution, and a Bernoulli distribution has one parameter, which is theta, right? And theta can range from 0 to 1. So that is the probability of heads. So what we are trying to learn now is we are trying to learn the best Bernoulli distribution, right? In general, we are trying to learn the best distribution, but as we discussed in the last class, that's a pretty big concept, hypothesis space. So we constrain it. We say we are only going to look at Bernoulli distributions, right? That makes it smaller. But even there, your concept class or your hypothesis space is infinite, right? Because this distribution is parameterized by theta, right? And theta can take infinite values between 0 and 1, right? So now how do we find the best theta? All right, so we'll look at that. All right, so the first thing we are going to look at is we can do it using the maximum likelihood estimation process, right? So what is the likelihood of a data set given that you know that it is a Bernoulli distribution? So let's look at that. So the topic is learning a Bernoulli distribution, right? So I give you my data set is basically draws samples from this distribution. That's my training data. So let's say it's H, 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 T, H, H, T, right? So these are the tosses that you have observed, right? Of course, Bernoulli distribution does not have to be limited to coins, right? But it could be ones, zeros, or anything else, right? But just for the sake of continuity, let's assume that this is what you observe. And now we need to know what is the theta. What is the theta, which is the parameter of the Bernoulli distribution, which generated this data set, right? Okay, so let's assume some theta. So then what is the likelihood of this data set? What is the probability of D given H or given theta? Now your H is theta, right? So this will be, typically we write it as, because all of these samples we assume they are independent of each other, right? So we can say it's I equal to 1 through n. What is the probability of one of these? So let's call these DIs, right? So DI given theta, right? So, and you must have already seen this before, but this can be written as theta raised to power number of heads that are there. So let's say the number of heads are n1 and n2 is the number of tails, and of course n is n1 plus n2. So this is typically written as n0. I'm using it n0. All right. So this is essentially, if you have n1 heads, then the probability of all those heads will be theta. So you multiply those, and the rest of them are tails. So the probability of tails is 1 minus theta. So raised to power, however number of tails we see, right? So now we want to do, we have seen that in the case of Bayesian, in the case of these limited concepts, what we did here was we chose the theta, we chose the H which had the highest value here, right? But so we can do, but here it was easy because we had only 10 values, so we could look and say, okay, which one is the highest, right? But now what we want to do is, because this is an infinite space, we need to find the theta. So we want to find theta for which PD given theta is maximum, right? So we want to maximize that because this is the likelihood. This is the likelihood. So we are trying to maximize this likelihood. That's why we call it a maximum likelihood estimation, right? So we can do it very easily. We can maximize it by just taking a derivative of this, setting it to 0. So we say d by d theta of p of d given theta, right, is going to be d by d theta of theta n1, 1 minus theta n0, right? You can write this to be n1 theta n1 minus 1 n0 plus n0 theta n1 1 minus theta n0 minus 1, and then when I differentiate this is going to give me minus 1, so I'm going to set this to minus, right? Then to get the theta for which this is maximum, we set this value to 0, so we set p d given theta equal to, sorry, d by d theta equals 0, implies that I'm just going to skip some steps, but n1 theta n1 minus 1 1 minus theta n0 is equal to n0 theta minus theta n0 minus 1, and if you solve this you'll get theta is equal to n1 over n0 plus n1. So this is the maximum likelihood estimate of theta. Sometimes we put a cap on top of it, hat on top of it, just to show that it's the estimated value, right? So any questions about this? This is just simple math here. But if you look at it, this makes sense, right? What is this? This is basically, you're saying that the theta is the number of heads that you observe divided by total number of observations, right? That, in fact, 2 classes back, I asked you, right? If I show you for these many heads and these many tails, then without doing any math in your head, all you would do is you'll say, okay, I saw 5 out of 7 heads, so the theta in this case will be 5 by 7, right? So even mathematically, it comes to the same thing, right? But this is something that we can make a computer do, so that's why we follow it, right? So this is maximum likelihood estimation. Any questions so far? So now remember, what we want, so we can actually stop here. We can say, okay, here is the estimate, right? Now when I get a new data point, right? So now if I get x star equal to 1 or heads, right? If I say, okay, so you can tell what is the probability of next heads, right? The probability of heads given you have observed this training data would just be theta MLE, right? Because you have estimated that your coin has this probability of a heads. So now the probability of next heads will be that. Yeah? So that is easy. So that is the MLE estimate or MLE procedure. So we do that I will do that again for a different type of distribution, but in general you could do it for any distribution from now on, right? All right, so let's keep moving. Stop me if anything is not very clear, right? Now the next thing we want to do, as we did in the last one, is to incorporate some prior. So what if we have some prior information about theta, right? What if, even though the example that I showed you today, the theta is coming out to be 5 by 7, right? But what if we want to say, typically theta is half, right? So we want to incorporate the prior here, right? So how do we incorporate a prior when your theta is infinite, right? Oh, sorry, when your theta can take infinite values, right? For example, remember in the past, right? If I go back here, so this is how we incorporated the prior in this case. But here it was easy because you only had 10 values. So you could say, okay, the prior probability of first one is 0.3, other ones is this and this. But if it takes infinite values, then you cannot specify one value for every possibility, right? So for that, there are 2 ways to do that. One is to put sort of a point prior, which is we say that, okay, prior probability is that the probability of theta to be half is 1. Prior probability, right? That's one way to do it. But that's not how Bayesians would do it, right? If you remember, Bayesians always say that everything is possible with different probabilities, right? So we don't want to have probability prior set like this. We want to have the prior also set as a probability distribution. Okay, so for example, in this next curve, right? So we want to set prior probability like this. What does this mean? This means that the probability of theta to be basically, if you read this, what it's saying is that it's more likely for theta to be towards 0.8, right? So we want to be able to set the probability like this, all right? So now how do we do that mathematically or statistically, right? So what we can do is we can come up with another distribution which we can use to represent your prior probability. So what do we need from this distribution is that the output, the sample of that should be between 0 and 1, and it should allow us to set some shape, right? So in this case, there is one distribution called beta distribution that we are going to use, okay? So beta distribution is going to be used as the prior probability distribution for theta, all right? And I'm going to demonstrate that to you quickly. So beta distribution is another type of distribution, just like Bernoulli distribution, Gaussian distribution. The probability, so the output, the sample of this distribution is theta, and it has two parameters, A and B. So like in Bernoulli distribution, you have one parameter theta. In Gaussian distribution, you have sigma, square, and mu. In this one, you have A and B. And the probability, then density of theta, this is a continuous distribution, right? So the density at theta is given by this number. All right, it is this. This capital B, it's a constant. It's called a beta function. So it is like a, you know what a factorial is, right? N factorial. So if you generalize factorials to real numbers, then that is done using a beta function. All right. So, but you don't have to worry about this part. Essentially, what this tells you is that that this has some shape. Okay. So this gives you the prior distribution. All right. Okay. All right, so let me go back to, well, I wanted to give you a, how does these A and B matter, right? So if you go back to your notebooks later on, there is a beta distribution in the SciPy library, right? So these are the two parameters of that distribution, A and B, right? So using different A and B, you can get different shapes, okay? So for example, if A equal to 4, B equal to 4, then you get this shape. What this shape is saying is, in terms of prior probability, is that I think that theta can take many values, right? It's a pretty smooth shape, but it's likely to be concentrated over here. But you can change the shape a little more. So for example, I can make this to be 16, both to be 16. And then you're sort of focusing your prior. You're saying it's more likely to be in this range. You can make it even higher. And then it keeps shrinking, right? So you can set it to, I don't know what, 1,000. So what this tells you is that you can shrink or expand based on what your prior beliefs are by just manipulating A and B, all right? You can also get other interesting shapes. So for example, if I set A equal to 8 and B equal to 2, you get shape like this. So which means that your prior belief is saying that theta should be around 0.8, right? You can set it other way, and it gives you this, right? So it's pretty cool. If you set A and B to be smaller than 1, then you get more interesting results. So this means it's saying that theta is, the prior belief that I'm adding, or prior probabilities, are that it's more likely to be either very high or very low, right? You can actually keep changing this like this. So you can even get like this weird distribution, right? So this is a way to set priors for theta. Any questions about this? Yes, go ahead. Good. So the question is how to set A and B. Now, since we call these priors, right? So we assume that this is given to us by somebody outside, like some expert, or somebody who has seen it in the past. So they say, okay, whenever I have seen, right? Think of some wise old lady who has seen a lot of Bernoulli trials over her life, and then she says, every day when I see it, theta either is here or here, and then you can set A and B accordingly. So there is no principled way to set it, but typically we call these kind of parameters hyperparameters. So these are what we set. So even in your assignment, the parameters like number of hidden units, the regularization constant, those all are hyperparameters, right? So we set it. Some of them we learn, like your weights. Okay, any other questions so far? Okay, great. So this is how we set it, right? Now one thing you can note is that the form of the probability distribution of theta, of this prior distribution, is very similar to the likelihood as well, right? Both have very similar form. Theta raised to n1, 1 minus theta n0, and in this case it's 1 over b theta a minus 1, right? So what we will see later is that this helps us in our mathematics, right? This helps simplify things a lot. And that is one of the reasons we use beta. So there are two reasons we use beta. One is that it lets us specify priors in many different ways. So I can set it here, I can set it here. Just by changing my a and b, I can set it to anything. However, another thing that it helps us do is it helps us make our math very easy. So we'll see how, right? So this is the likelihood of the data given theta, right? This is the prior probability of theta using the beta distribution, right? I have put a proportional sign here because I have ignored that b constant. So remember, I'm going to switch back. So the actual probability of prior probability of theta is actually 1 over b this, but this is a constant, right? Given a and b, this is some number. So we don't care about it. So we say that the prior probability is just proportional to this value, yeah? So if I want to compute the posterior, remember the posterior is likelihood times prior divided by some constant factor. That is basically multiplying these two numbers, right? So if I multiply these two numbers, because they have such similar form, it will look like this, right? Which means that the posterior of theta also looks like a beta distribution. Remember? So the prior is a beta distribution. The likelihood of d given theta is this. So the posterior distribution of theta also has a form like this, right? So it makes it very easy to understand. So you started off with some beta distribution as your prior. You had some likelihood of your training data, and then you revised your estimate, but the output is again a beta distribution, right? So which means that posterior has the same form as the prior. So when that happens, we say that the prior distribution is a conjugate prior for the Bernoulli distribution, right? So we assume that your training data is being generated from a Bernoulli distribution, right? Because it's a coin tosses. And we assume that your prior has a beta distribution. And when you compute the posterior, it is again the beta distribution, right? Which means that your prior and likelihood are conjugates of each other. And this is a very important concept when you look at other forms of Bayesian classifiers. We might not look at them in this class so much, but this is a very useful concept, because what this helps us is it makes this equation beautiful, right? If this were not the case, right, then it would have been very hard to compute, mathematically compute it, right? All right, so as we said that the posterior is essentially also a distribution like this. So I mean, I'm going to do it here as well. Any questions so far? So remember, so what we did was we said that we assumed that theta, the prior on theta, is actually a beta distribution which has two parameters a and b, and the density function for that is a minus 1 all right. And then we said that the probability of d given theta, which is the likelihood, is that we have already seen theta, the number of heads we see times the number of tails we see, yeah. So remember the equation for the posterior for theta will be probably, this is basically the Bayes rule, right? P theta, P d given theta divided by, right? Typically we write summation, right? We say all other thetas, with theta prime. That's how we do it, right? However, in this case, because theta can take infinite values, we replace this by an integral. So this is equivalent of for all thetas d theta, right? However, what you can see is that this is kind of like a constant value, right? So we don't really care about it that much if you want to just find the best theta, yeah? So what we can say is that So we can think of this as another constant. So this is some k. Okay, 1 over k p theta is this. So it is some other constant b a comma b theta a minus 1, and then this is theta n1. So which means that the posterior also has some. I'm combining this as a constant. So 1 over k1. All right. Any questions? All right. So that's why we call them the conjugate priors. So now we have three things now, right? We have the probability, we have the probability distribution, we have the likelihood of the data set given each value of theta, and we have this, right? So now the question becomes how do we, because my burning question is the probability of a new data point to be heads given this data set, right? So as I showed you in that other example, this can be written as what is the probability of h given my theta is coming from the prior, the best prior, right? Or probability of x star to be h given my theta is coming from the MLE, and x star to be h, theta is coming from map, and then the last one is the Bayesian one, and we'll talk about it. All right. So you can do all of these, right? So you can find what is the best value for theta given this, right? And that's easy to do if you basically again do the same thing. You maximize it, right, for theta, right? If you're trying to find the best prior probability which gives you the highest value for this, you can maximize it, and the math is the same. So the theta prior actually will be a minus 1 over a plus b minus 2, right? That's easy. This I have already shown you. This is theta MLE. This will be n1 over n0 plus n1, right? And then you can also compute this, right? You can also maximize this to get the theta map, and that also is fairly easy because the math is exactly the same. The map will just be n1 plus a minus 1 over n1 plus n0 plus a plus b minus 2, right? Because you're just doing that. Okay. Any questions so far? So now what you can do is, now if somebody asks you, okay, what is the probability of getting heads? If you're using prior, then you'll say the probability of getting heads is this. Probability of getting heads if you're using MLE is this. Probability of getting heads if it's a map, it is this. Yeah. So that's easy. Now we will look at, okay, how does the Bayesian averaging work? Any questions so far? Yes.
So what is the derivative of now single solution?
I'm sorry, you have to repeat it.
Let's say you have many maximums, like the derivative of two solutions.
Oh, I see. So the question is that what happens if you have multiple maximas, right? Well, at least in this case, that won't happen because, oh, you're saying even for the beta distribution, you could have multiple maximas, right? You're right. Yeah, so then that actually is a good motivation for doing Bayesian averaging. But in general, beta distribution tends to be smoother, except when it's like that. So then you will have one maxima. But yeah, so we'll look at Bayesian averaging. That's an excellent point, right? Because the probability distribution could be anything, right? And you want to find the maximum value. So if there are multiple maxima, then you are stuck, right? But Bayesian averaging lets you handle that as well. Okay. So let me see what else I want to talk about.
What's good in there? Under the theta MAD.
Over here?
Yes.
Oh, sorry. And this is illegible. Basically, this is, if you maximize this, right? So I'm going to write it. So the posterior distribution for theta looks like this, right? Because these are conjugates, so they just get multiplied. So if you maximize this, you set the derivative of this to be 0, it follows the same math as we saw earlier, then that comes out to be, let me write it cleanly, n1 plus a minus 1 over n1 plus n0 plus a plus b minus 2. All right? Okay. Like this? All right. Any other questions? All right, fantastic. So the next thing we want to do, so now we have looked at 3 ways, but now we want to say, can we do it using the Bayesian average, all right? So instead of writing it, I'm a little tired today, so I have all the math here, right? So this is the Bayesian approach, the Bayesian averaging approach. So here we assume that all theta are possible. Instead of just choosing the max theta, right, what we do is we look at all possibilities. So we want to know what is the probability of x star to be 1 or heads given d. So we say, let's choose all thetas that we have, and then but multiply them with the probability of those. So this is exactly like what we did in Bayesian averaging, except we have an integration here because theta can take infinite values. And if you work this math out, what will happen is that essentially what is the probability of heads given theta will be theta itself, right? Because it's a coin toss. We are assuming that this is a Bernoulli distribution times this p theta given d. Now remember that p theta given d, the posterior, is a beta distribution. So this is actually just the expected value for the posterior distribution, right? Because that's how the expected value is written. The expected value for any distribution is theta times p theta d theta integration, right? So that's this. I have a slight mistake here. This should be theta comma d, because this is probability of x given whatever theta and d we have seen. All right. So this actually comes to be expectation of this, and expectation of this has this form, right? So this is the Bayesian estimate. So let's go back. Let's go back to here. So I'm not going through the math because the math fairly is pretty straightforward here. It's just integration. But the idea is that for the Bayesian approach, so remember p x star is equal to heads or 1 is just the integration of p x star equal to h given one of the options, then probability of that and d theta for overall theta. This works out to be the expected value of this random variable, which is theta. And since this is a beta distribution, there is a known answer for that. That is just a plus n1 over a plus b plus n0 plus n1. In the slides, I have n, which is this plus this, right? So this is another probability. So what we have seen so far is that you can get 4 different answers. You can get this, which is theta prior is basically n1 over n0 plus n1. This will be n1 plus a minus 1. Sorry. This is a minus 1 over a plus b minus. This is a prior. This is n1 over n1 n0 plus n1. And this is n1 plus a plus minus 1. I have it written in the slides as well, so don't worry about thing. And so essentially what I want to tell you is that you can get the probability of heads in 4 different ways. Each one of them uses a, n1, b in different way. All right? Any questions so far? So in the exam, if I ask you, what is the probability of heads given assuming the map, right? You use this formula. If you use something else, use the other formula. In general, you can extend this. You can say, okay, instead of using beta as my prior, I have some other distribution as the prior. Then all that will happen is your math would change and these expressions would change, but the approach is the same. You just maximize it under different conditions. All right. So one interesting thing that I want to mention before we end today is that why do we use a prior, right? Remember, we use, I kind of mentioned it that the reason we use prior is because it helps us incorporate expert opinion, right? Another way to motivate that is that, let's say you have this as your training data, tails, tails, tails. You see 3 tails, right? So n1 is 0 and n, which is n1 plus n0 is 3. So then the theta of MLE will be 0, right? Which means the probability of observing heads is 0. Why? Because the formula for theta MLE is somewhere I had all the expressions. Well, it is n1 over n1 plus n0, so which is 0 over 3, right? Which means that since you have never observed a tails, from now on your outputs will always be, you will always expect a tails to come. So the probability of observing heads is always 0. So this is what is also known as black swan paradox. If you read the book called The Black Swan, I know, by Taleb, right? So he talks about this as well, which is that if you have never observed something, what the MLE estimate says is that it basically tries to follow the training data. So it has the same flavor as overfitting. So you're following the training data. What happens with, what happens with the prior is that prior helps us sort of give a non-zero probability even if you do not observe a heads. Remember, so if we go back here, right? So by incorporating the prior, like here or here, even if your n1 is 0, right? You have not observed any heads, you will still get a non-zero probability of a heads. So that is how you sort of accommodate this kind of a spurious training data. So your training data might tell you something, but maybe you do not want to believe the training data completely, right? So the prior helps you sort of do this control over the overfitting process.